Question 6b, first part. Determine algebraic and geometric multiplicity of each eigenvalue of the matrix. So first of all, of the given matrix, so first of all we want to find eigenvalues. After that, corresponding to that eigenvalue, we have to find eigenvector. Okay. Now, if lambda 1 is an eigenvalue, okay, occur in one time, so algebraic multiplicity of lambda 1 is 1. If lambda 1 is an eigenvalue occur in 2 times, then algebraic multiplicity of lambda 1 is 2. So algebraic multiplicity is depending upon the how many times that eigenvalue occur, right? Now geometric multiplicity is depending upon the corresponding to depending upon the eigenvector corresponding to that eigenvalue, that how many eigenvector we have corresponding to that eigenvalue. Suppose corresponding to lambda 1, corresponding to eigenvalue lambda 1, we have one eigenvector, so geometric multiplicity of that eigenvalue is 1. Okay, and suppose we have corresponding to lambda 1 we have two eigenvectors, so the geometric multiplicity of that eigenvalue is 2. Okay, so just try to understand. You can also see the definition of the geometric and algebraic multiplicity in any book. So here just an example, we want to find algebraic and geometric multiplicity of each eigenvalue of the given matrix, and this question asking 3 marks. So first of all we find eigenvalues of the given matrix, and for that we use characteristic equation. Determinant of a minus lambda I is equal to 0, or you can also use this method. Here is the 3 cross 3 matrix, so the characteristic equation you can directly with this method, lambda cube minus s1 lambda square plus s2 lambda minus determinant of a equal to 0, where s1 is equal to trace of a. Trace of a means addition of the main principal diagonal elements. So main principal diagonal elements are, you can see 1 2 2, so just add 1 plus 2 plus 2, that is 5. So first two part you have lambda cube minus 5 lambda square. Now to find s2. Now what is s2? S2 is the coefficient matrix of the main principal diagonal elements, that is coefficient matrix of the first element, that is 2 1 2 2 1. Okay, coefficient matrix of the first main principal diagonal element, that is 1. So remove that column and row in which that 1, so you will get 2 cross 2 2 cross 2 determinant 2 1 2 2. Then coefficient matrix of second main diagonal element, that is 2, so you will get another 2 cross 2 determinant, that is 1 2 minus 1 2, and then third determinant is 1 2 0 2. Addition of that 3 matrices, that will become 2 plus 4 plus 2, that is equal to 8. So s2 is equal to 8, and then final determinant of a. Here is the determinant of a, that is 1 2 2 0 2 1 minus 1 2 2, that is equal to 1 into 4 minus 2, that is 2, minus 2 into 0 plus 1, that is 1, plus 2 into 0 plus 2, that is 2. So 2 minus 2 plus 4 is equal to 4. The characteristic equation of a is lambda cube minus 5 lambda square plus 8 lambda minus 4 equal to 0. So lambda 1 into lambda minus 2 square is equal to 0. The eigenvalues of a are 1 2 2. So the eigenvector x, x1 x2 x3 corresponding to the eigenvalue lambda is given by the matrix equation a minus lambda I into x is equal to 0. So we have 1 and 2 are eigenvalues, 1 occur in 1 times and 2 occur in 2 times. That you have to mind it. So now we want to find eigenvector. First of all, corresponding to lambda is equal to 1. So here is the characteristic, here is the matrices. The eigenvector x corresponding to the eigenvalue lambda is given by the matrix A minus lambda I into x is equal to 0. So here is the A minus lambda I into x is equal to 0, that is 1 minus lambda 2 2 0 2 minus lambda 1 minus 1 2 2 minus lambda into x1 x2 x3 equal to 0 0 0. Take lambda is equal to 1 in the given matrix. So 0 2 2 0 1 1 and minus 1 2 1 into x1 x2 x3, that is equal to 0 0 0. Solving this matrix, you will get 2x2 plus 2x3 is equal to 0, x2 plus x3 is equal to 0, and minus x1 plus 2x2 plus x3 is equal to 0. Take x2 is equal to minus x3 and x1 is equal to minus x3. You will get x1 is equal to x2 is equal to minus x3. So taking x1 is equal to minus 1, we get x1 is equal to x2 is equal to 1. So thus the eigenvector corresponding to lambda is equal to 1 is 1 1 minus 1. Take lambda is equal to 2 in equation 1, minus 1 2 2 0 0 1 minus 1 2 0 x1 x2 x3 is equal to 0 0 0. So minus x1 plus 2x2 plus 2x3 is equal to 0 and x3 is equal to 0, minus x1 plus 2x2 is equal to 0. So take x1 is equal to, you will get x1 is equal to 2x2 and x3 is equal to 0. So taking x1 is equal to 1, x2 is equal to, taking x2 is equal to 1, x1 is equal to 2. So the eigenvector corresponding to lambda is equal to 2 is 2 1 0. Now you can see we have 1 and 2 eigenvalues, 1 occur in 1 times. So that's why algebraic multiplicity of 1 is 1. 2 occur in 2 times as an eigenvalue. So that's why algebraic multiplicity of eigenvalue 2 is 2. Now corresponding to lambda is equal to 1, corresponding to 1 we have only one eigenvector. So that's why geometric multiplicity of eigenvalue is 1. Now 2 occur in 2 times as an eigenvalue, but corresponding to lambda is equal to 2, we have only one eigenvector. So that's why geometric multiplicity of eigenvalue 2 is 1. Okay, and geometric multiplicity is always less or equal to algebraic multiplicity. That just keep in mind that geometric multiplicity is always less or equal to algebraic multiplicity. So here is the final answer, that algebraic multiplicity of 1 is 1 and 2 is 2, and geometric multiplicity of 1 is 1 and 2 is 1. Okay, so here is a complete this question. And next question, question number 6b. Here is a definition. Hermitian matrix. Define 3 definitions. That first one is Hermitian matrix, second is unitary matrix, and third one is normal matrix. Here is the definitions. First one is Hermitian matrix. A square matrix A, Aij, is said to be Hermitian if ijth element of A is equal to the conjugate complex of the jith element of A. That means small aij is equal to AJI bar. Bar means conjugate of that element for all ij. Let's take one simple example of Hermitian matrix. You can understand very well. Let's take A is equal to 1 plus I, 1 and 1 minus I. Okay. Now Hermitian matrix means A is equal to A star. If this thing happen, we can say that A is Hermitian matrix. Okay. Now A is equal to A star means, first of all, A star is what? A star is first of all we conjugate of the given matrix and then transpose, or either you first transpose and then conjugate, both are same. Okay, you can also write down A transpose and then conjugate, this both are same. Okay, so let's take first of all we conjugate of the given matrix. 1 plus I become 1 minus I, 1 as it is, 1 as it is, 1 minus I become 1 plus I. Okay, now we transpose, that is A star, that is 1 minus I, 1 and 1, 1 plus I. Now this is not equal to A, you can see these two matrix are not same, so this matrix is not an Hermitian matrix. But if you take 1 plus I here and 1 minus I here and 1 1 here, that matrix become Hermitian matrix. Okay, if you take, see, if you take A is equal to 1 1, 1 plus I, 1 minus I. Now what is A bar? That is 1 1 minus I, 1 plus I and 1. Okay, and whenever you transpose 1 1 minus I, 1 plus I, 1, now this is equal to A star, that is exactly the A. These two matrix are same, so this matrix is Hermitian matrix, you can see. Okay, this matrix is an Hermitian matrix. So this is one simple example of Hermitian matrix, so you can understand. Okay, now next is a unitary matrix. A square matrix A is said to be unitary if A into A star, that is equal to identity matrix, equal to A star into A, where A star is already I defined using the example. You can also understand that what is A star, meaning of A star, that is transpose of the conjugate matrix, right, or conjugate of transpose of A. Now next is normal matrix. For normal matrix you just need this condition, A into A star is equal to A star into A. Either it's identity matrix or not, that doesn't mean, but using these three definitions you can also understand that every unitary matrix is normal matrix always. Okay, but to become unitary matrix it's more specifies that it should be identity matrix. Okay, so A into A star, that is should be identity matrix, so that is important. So these three definitions, this question complete. Now next question, question number 6C. If A is equal to 1 2 minus 3 0 2 3 0 0 2, then the eigenvalue of A transpose and 5A. Now first of all we find A transpose and 5 into A. So what is A transpose? Just changing the row and column, interchange the row and column. So A transpose is 1 0 0. I reading this by row wise. So first row is 1 0 0, 2 2 0 and minus 3 3 2, 5A equal to 5 10 minus 15 0 10 15 0 0 10. A transpose is an lower triangular matrix and 5A is an upper triangular matrix. So we know that eigenvalues of the triangular matrix are the elements of the main principal, its principal diagonal. Okay, so the eigenvalues of A transpose, you can see A transpose is lower triangular matrix and 5A is an upper triangular matrix. So and in any triangular matrix the eigenvalues are exactly the main principal diagonal elements. So the eigenvalues of A transpose are 1 2 2 and the eigenvalues of 5A are 5 10 10. Okay. Question number 7. A, first part is T from R3 to R3 defined by T of x, y, z is equal to x minus y plus z. First coordinate, second coordinate is 2y minus z, third coordinate is 2x plus 3y. So just try to understand that x minus y plus z is first coordinate minus second coordinate plus third coordinate. 2y minus z can be understood as 2 into second coordinate minus third coordinate, and 2x plus 3y can be understood as 2 into first coordinate plus 3 into second coordinate. Is it linear or not? And the next question is, T is one word or not? So here is a solution. Let x is equal to x1, x2, x3, y is equal to y1, y2, y3. So x plus y is equal to x1 plus y1, x2 plus y2, x3 plus y3. So T of x is equal to x1 minus x2 plus x3, 2x2 minus x3, 2x1 plus 3x2. T of y is equal to y1 minus y2 plus y3 and 2y2 minus y3, 2y1 plus 3y2. So let's find T of x plus y. Now T of x plus y means T of x1 plus y1, x2 plus y2, x3 plus y3. That is exactly the using the definition of T, we can define T of x plus y, that is equal to x1 plus y1 minus x2 plus y2 plus x3 plus y3. First coordinate, second coordinate is 2x2 plus 2y2 minus x3 minus y3, and the third coordinate is 2x1 plus 2y1 plus 3x3 plus 3y2. Now that is equal to that can be written as x1 minus x2 plus x3, 2x2 minus x3, and 2x1 plus 3x2 plus y1 minus y2 plus y3, 2y2 minus y3, 2y1 plus 3y2. So T of x plus y is equal to T of x plus T of y. For alpha belongs to R, second condition is also satisfied. You can see T of alpha x can be easily, you can solve alpha into T of x with some simple simplification. T of alpha into x, that can be written as T of alpha into x1, x2, x3, that is T of alpha x1, alpha x2, alpha x3. Now use the definition of T, that is first coordinate minus